This is Lab 5 for Physics 1. I chose to do something similar to the solar system suggestion WebAssign had. The purpose of my lab was to accurately model and predict the length of the Earth's orbit around the Sun in a year using Newton's second law. My result was that my calculated length of a year was fairly accurate because it was within 2 days of the actual length of a year. This was obtained by calculating the net force using Newton's second law of universal gravitation, then finding the velocity, then finally using that to predict the position. The very first thing I did was specify my initial conditions. Here are some knowns I used. I set up the scene so that it was large enough to see the Sun, Earth, and Earth's orbit, then created the Earth and Sun by making two spheres. It is important to note that the scale used to size the radius of the Earth and Sun in VPython was not accurate. I used a much larger radius for the Earth and the Sun so I can ensure they would both be visible in my model. It is okay to not have the radii of the Sun and Earth be to scale because I am not using those values in any calculations. I then added in the mass of the Sun and Earth, which I also specified on the previous slide. I wrote this right here in order to show the orbit of the Earth. I then went on to calculate the velocity of the Earth. The velocity could be found in the chart with planetary information provided to me at the start of the lab by a website WebAssign suggested. But in order to obtain the most accurate velocity and to show you the calculations of how it is found, I chose to calculate it on my own. So I started with Fgrav is equal to Fnet. Then I went on to replace Fnet with the formula for centripetal force because the motion is circular. So instead of saying F equals ma, we can say F equals mv squared over r. I continued simplifying, and as you can see here, I listed all of my steps until I got v equals square root of g times the mass of the Sun all over r. I then proceeded to write this formula into VPython, which you can see right here. Since r stands for the distance between the center of the Sun and the center of the Earth, I needed to specify what that was, which you can see right here. I picked delta t to be 86,400 times 3 because relative to the length of a year, 3 days is still small, but it is not small enough that the program takes forever to calculate the length. The next step was to model the motion of the Earth by showing its orbit. This was done by applying Newton's second law repeatedly in a while loop. I made the time of the while loop be 86,800 times 365 because I needed to make sure the model would show the entire orbit. I needed to put r equals earth.pos minus sun.pos into the while loop because each time it moves, the magnitude is staying the same, but the direction is changing, so I needed to account for every time it changes. Next, I needed to calculate the gravitational force acting on the Earth. One assumption I made was that Fgrav is the only force acting on the Earth. The gravitational effects of the other planets do not need to be accounted for because they are so small compared to the Sun's effects, so I didn't include them in the model since they really weren't relevant to the question I was asking either. You can find Fgrav using the formula that you see right here, which is just Newton's law of universal gravitation. Next, I updated the position of the Earth. I started with F equals ma, which manipulated gives you a equals F over m. Then to update the velocity, use the formula that you see right here, which you then use that velocity to update the positioning. Then this part right here with Earth.orbit is in order for the orbit to show up so we can see the motion. Now my question was about predicting the time it takes for the Earth to fully orbit the Sun, also called the period t, or more commonly known as a year. To find that period, I had to derive v equals 2 pi r over r, which is essentially velocity equals circumference of a circle over the period. Now we know from the previous derivation that this equation right here is true, so we can set these two equations equal to each other. My steps are written in the order that you see here, and eventually you get that t equals 2 pi square root r cubed over g times n. You can see the code for this on the next slide. But I actually want to show you the model first, and then we will talk about the code. So this is the model that you get. The middle will be the Sun, and you can see this is the Earth, and the orbit is very circular, and here's where you're going to get your results. So in order to get this image, here's where I plugged in the equation I derived for t. I printed the number of days I calculated it would take the Earth to make one full rotation around the Sun, which is the time of 1 year. My calculated value is approximately 3,169,1036 seconds. In order to find out how accurate my calculated number was, I calculated the difference in the number of days between my calculated length of a year and the actual length of a year. I found the difference to be approximately 1.79 days, which if you think about, compared to a whole year is an extremely small difference, which means my calculated value of the period was fairly accurate due to it being within 2 days of the actual length of a year. However, it's important to remember that the calculated period will not be completely accurate because I assumed that the gravitational force of the other planets on Earth was negligible due to the gravitational force of the Sun being so great. That is why the orbit looks pretty circular when in reality it is slightly more elliptical, with an eccentricity of 0.0167. My first what if question was what would happen to the period if the mass of the Sun was doubled. As you can see on the screen, when I applied the change to my code, I got a period that was roughly 1 e to the 7th smaller than my normal period, and the difference in the number of days between the actual and calculated length of a year was much larger. I'll explain why in 1 minute. The second part of this question was what would happen to the period if the mass of the Earth was doubled. As you can see on the screen, when I applied the change to my code, I got a period that was the exact same as the original period, when neither of the masses were doubled. Now the answer of why to both of these questions goes back to our previous derivation of the formula for t. When the mass of the Sun was doubled, the m that you see down here became a lot bigger, making t, the time it took for the Earth to go around the Sun one full time, a lot smaller, and therefore faster. When the mass of the Earth was doubled, it didn't change anything, because if you'll notice in the final equation for t, there is no little m, which stands for the mass of the Earth. If you remember, it canceled out right here. And when we were calculating the formula for the velocity, that allowed us to set these two equations equal to each other. So So the mass of the Earth had no impact on the period, while the mass of the Sun did. My second what-if question was, what if there was no gravitational force between the Earth and the Sun? Well, since the orbit of the Earth is caused by the gravitational pull of the Sun and the Earth's velocity being at a right angle to it, the Earth would have continued forwards in a straight line if that gravitational pull was eliminated, rather than the Earth going in an orbit around the Sun. My what does it mean question was, why could you assume that the gravitational force from the other planets in the solar system was negligible? How would that have affected the orbit if it wasn't negligible? The mass of the Sun is so big that the gravitational force it is exerting on the Earth is much bigger than the gravitational force the other planets could be exerting, so the other planets' forces were negligible. The orbit would have been more elliptical if the gravitational forces from the other planets had been taken into account, rather than as circular as it came out, which you guys saw in the model. And that is the end, so thank you so much for listening and watching.